Hello, I'm Michelle Crummell, and in this lesson we are going to look at how to estimate solutions to differential equations using slope fields. In the last lesson, we saw how we could solve a differential equation using a technique called separation of variables. But I have an example here. It's a differential equation, dy dx equals x plus y, and in this example we are unable to separate the variables. We could try and multiply both sides by dx, but then we would get dy equals x plus y dx, like so, and we're unable to move that y over to the left-hand side. If we tried moving it to the left-hand side first by subtracting it, we would have dy dx minus y equals x. Now we can't get the dx by itself on the right-hand side. If we multiply both sides by dx, we would end up with dy minus y dx equals x dx. So there's no way to separate the variables in this particular differential equation. So what we're focusing on today is how we can estimate solutions. Even if we're not able to solve the differential equation algebraically, we can estimate solutions graphically using something called a slope field. So even though we don't have the solution, y equals f of x, right? We don't know the function that y is equal to, we still have a lot of information from this differential equation. We know what the derivative of the y equation is at any point along the curve, because we know dy dx is just equal to the x coordinate plus the y coordinate. So we can, for example, conclude at the point 1, 1, the slope dy dx would just, at the point 1, 1, would just be 1 plus 1, or 2. So it has a slope of 2. So even though we don't know what the graph of y equals f of x looks like, we know what the graph of its tangent line looks like at that particular point, and that gives us some information about where the graph is and what it's doing and how it's changing. And we can find the derivative at multiple points along the curve. So in this example, we are calculating the slope at the point 1, 1, 1, 2, 1, 3, 1, 4. Now, those points might not all be on the same graph of y equals f of x, but we could pick any point in the plane and substitute the x and y coordinates into this differential equation and figure out, okay, if this is a point on the graph, here's what the slope of the graph would be at that point. So we know the slope of the curve even if we don't know the equation of the curve. And that's actually really helpful. A slope field is a visual representation of all the possible solutions to a given differential equation. It tells us the slope at any given point. So these little lines that you're seeing in the slope field graph actually represent tangent lines. Now they're just little segments of the tangent line. We're not drawing the entire tangent line because then all of the lines would just be intersecting and we would just end up with basically a big black blob. We also are only calculating the slopes at certain values of x and y here, right? And that's your choice. So for right now, in this example, we're calculating in increments of 1. So we have slopes, for example, at the point 1, 0, at the point 2, 0, 3, 0, 2, 1, 1, 1, and so on. Those slopes have been calculated and the little tangent lines drawn to indicate what the slope of the curve would be at that point. So if the graph passes through this point, we know basically that it would look like this in that little area of the graph. The tangent line is pointing us in the direction of where the graph is headed. Remember, tangent lines can be used to approximate the graph of y equals f of x as long as you stick close to the point of tangency. So as soon as we get near a new point of tangency, we would want to adjust the shape. We can't just assume that if the curve passes through this point, then the curve just looks like this. Obviously it won't. We can see that the slopes are changing as we move further to the right. Okay, they don't look like, here it looks more like this, and then here it looks more like this. And so think of the little slope marks as just pointing us in the direction in which we need to go, and then as we get closer to a new slope mark, we adjust and we change direction slightly to go in the new direction. For this, if we stick with this example, if the graph does pass through this point 1, 1, then I can say, okay, it's moving along this way, and then I'm readjusting as I'm getting close to these other slopes. I'm moving in the new direction of the new slope there. and coming down this way. So now my eye is drawn towards this one here, and I'm readjusting. And then it's kind of difficult to see, but there's a little horizontal slope right there. So that's telling me, oh, turn and go horizontal. And then, you know, I'm sort of looking at halfway in, I'm going to split the difference here and go halfway in between the direction that those two are pointing. And then I just end up, now I end up here along this. Is actually a slant asymptote. And that would be what my graph looks like. Versus if we knew that the graph passed through this point right here, I'd start going this way, and the slopes are really not changing that much. So pretty much stick to that same direction. Going backwards, I'm going this way, turning slightly, and heading off like that. So the graph can look very different depending on which point it's passing through. And so in order to sketch the solution in the slope field, you do need to know at least one point on the graph of your function y equals f of x. Otherwise, you know, we have no idea where the graph, what points the graph could be passing through. So let's practice sketching a slope field. If we're given a differential equation, we can create the slope field just by calculating slopes at different points. So for example, if I want to know what does the slope mark look like at the point 0, 0, I'm just going to substitute 0 in for x and 0 in for y. You just substitute your x and y coordinates into the differential equation and compute the slope. Now there's something interesting about this differential equation. The slope is just equal to x minus 1. There's no y variable there. The slope is solely dependent upon the value of x, and it is not influenced by the value of y. So the y coordinate is insignificant. It's only the x coordinate that's going to determine the slope. And so what that means, let's say, for example, I'm going to check when x is equal to 1. Let's say I'm interested in this point right here, 1, 1. The x coordinate is 1. So the fact that y is 1 really is irrelevant because the slope is determined by the x coordinate in this differential equation. And so the x coordinate is 1. And when I substitute in 1, I get dy dx equals 1 minus 1 equals 0. The slope is 0. And what does a slope of 0 look like? What would the tangent line look like if the slope is 0? Well, it would be a horizontal tangent, so it would look like that. And anywhere that the x value is equal to 1, that's going to happen. I'm going to get a slope of 0. So down this entire column, the x coordinate is 1. And it doesn't matter what the y coordinate is. If the x coordinate is 1, the slope is 0. So I can very quickly fill in the slope field for that entire column where x is equal to 1. And this kind of differential equation is called an autonomous differential equation, where it's just solely expressed in terms of x and not in terms of y. And so we can very quickly fill out, it looks like there's a lot of points to fill out, right? We definitely don't want to just say, okay, substitute in the coordinates of this point, then the coordinates of this point, then the coordinates of this point. It would take a very long time to create the slope field that way. So we want to do this efficiently. So let's use x equals 2. If x equals 2, the slope is 1. So everywhere x is 2, in other words, this entire column right here, everywhere that x equals 2, the slope is equal to 1. And a slope of 1 is easy to draw because it's just a 45-degree angle. So that one's not too tricky. Now, how about when x is 0? When x is 0, if we substitute in 0, we get a slope of -1. And a slope of -1 makes a negative 45-degree angle. So down this entire column, you know, I'm doing it kind of quickly, but the slopes should all be parallel. Then when x equals -1, we have a slope of -2. So -2 is steeper than -1. We don't want to draw it at a negative 45-degree angle. We want to make it look a little bit steeper. And I don't know how to do this show you this on the iPad, but a good way to do this is to take the edge of a piece of paper or a ruler or an index card. If you are at this point right here and you need to draw a slope of -2, put your ruler up against this point, and then a slope of -2, you can go down 2 and over 1, which would take you to this point. And so you're going to line up your ruler through those 2 points like that, and then draw your little slope mark right there. So I need to erase that. Okay, so then I'm going to just draw these, try and make them parallel. And we'll say that's a slope of -2. When x equals -2, then the slope is equal to -3. So this needs to get even steeper. slope of -3. So we're going down 3, right 1 to do those slopes. And there is my slope field. So here's what that slope field actually looks like. I think it did a decent job. Now we want to sketch the solution curve that passes through the point -1, 1. So let's find the point -1, 1. That's this point right here. And we're going to sketch the solution curve. So I'm going to start just going to the left. I'm going in the direction of this little slope field mark. So this tangent line, it's telling me to go in this direction. And then I'm kind of readjusting as I go up. Now, it's okay if you're off a little bit from the way that I drew mine. You shouldn't be too far off, but it doesn't have to be, exact. We don't have a whole lot of points to work with here, and our slopes are pretty spaced out, so it's hard to know exactly how to draw it. Now let's go from this point, let's go to the right. So we're going to go in this direction, and I'm readjusting as I go. And I can see that the slope is flattening out here when I get to x = 1, turning and then coming back up this way. So at the end, I went a little too steep there. It's probably more like this. Now this differential equation is one that we can solve. If we wanted to solve this differential equation, we could. We could separate the variables. We've got dy equals x minus 1 dx. We've separated the variables. We can integrate both sides. We get y equals x squared over 2 minus x plus c. And then we can solve for c because we know that the graph passes through this point, -1, 1. So 1 equals -1 squared minus -1 plus c. So c equals -1/2. And then if we substitute that into our general solution here, we get y equals 1/2 x squared minus x minus 1/2. And if this is the particular solution, if you graph y equals 1/2 x squared minus x minus 1/2, it should look exactly like what we drew here, if we drew it well, right? So this is the actual solution, and it should match the graph that we just drew. For our next example, we want to sketch the slope field for dy dx equals x minus y. This is one that we're not going to be able to solve using separation of variables, so we can't really check our graph in the end. We'll just do the best we can. So we're going to calculate some slopes, and this one is not autonomous. The slope actually depends on both x and y, so we're going to have to substitute in the x and the y coordinate. But again, I don't want to just substitute in those coordinates, then those, then those, then those, then those. Like, there's a lot of points on this slope field graph. I want to do this efficiently. So what I like to do is ask myself, which points are going to give me a slope of 0? And I can tell from the equation here that the slope is going to equal 0 whenever the x coordinate and the y coordinate have the same value. So those are going to be points like 1, 1, 2, 2, 3, 3. And I'm going to have a slope of 0 at those points. So 1, 1, 2, 2, 0, 0, -1, -1, -2, -2. Okay, so I was quickly able to get 5 of those just by thinking about it that way. Then the next thing I'm going to ask myself is, well, when am I going to get a slope of 1? Because that's easy to draw also. It's just a 45-degree angle. So we're going to have points like 1, 0, where the x coordinate is 1 higher than the y coordinate. 2, 1. We don't have any x coordinates of 3 in our window here, so let me back that up. It'd be 0, and if that's 1 higher, then this would be -1. And let's just go ahead and plot those. So 2, 1 has a slope of 1, 1, 0, 0, -1. Now I can see now a pattern. This is along the diagonal here. I didn't draw that one terribly well. There and there, like so. Okay, now how about a -1? Well, that would be when y is 1 more than x. So points like 0, 1, right? Because 0 minus 1 would give me -1, or 1, 2, or -1, 0. So let's plot those points. So -1, 0, that's a slope of -1. It's going to look like that. 0, 1, 1, 2. So this also seems like it's happening on the diagonal here. And the rest of them, I think I'm just going to just plot the points. Okay, so I'm going to work in the fourth quadrant. I need 1 and -1. I'm subtracting. So 1 minus negative 1 is 2. So I need to make that steeper than this because that's a slope of 1. I need a slope of 2. So make that, and then I'm going to try and go along the diagonal and see if I'm still getting, the same. So let's try this 2, 0 next. 2, 0 is a slope of 2. I'm substituting in here, 2 minus 0. And then 0 and negative 2, 0 minus negative 2, yep, that's a slope of 2. So I'm pretty confident that it's going on diagonals. Then 2, negative 1 is going to give me a slope of 3, so it's getting even steeper. I don't know if that is a slope of 3, but I'm just trying to make it, it's going to go steeper, 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 like so. Okay, 1, 3, let's do this point up here. 1, 3 is going to give me a slope of negative 2. So here's like negative 1. I need to be more like that for negative 2. More like that. And then 0 and 2 is also going to give me negative 2. So it's going to go along the diagonal, negative 2. I'm trying to make them look parallel along that diagonal. 0, 3 is going to be negative 3, so it's going to get steeper, steeper, even steeper here, even steeper here. Okay, so that might not be perfect, but I think it's pretty close. Here's what that slope field actually looks like. And we are asked to sketch the solution that passes through the point negative 1, 1. So here's that point, negative 1, 1. And I'll go to the left first. So following the direction of that tangent line, readjusting as I go, just slight readjustment there. The slopes are not changing that much. And then going to the right, we're going down this way. And now my eyes are saying, okay, kind of split the difference here. So I'm going in this direction. I can see right here, it's hard to see, but there's a horizontal tangent right there. So there's a turning point I'm going to hit, and then I'm going to come up here, and now I have to kind of split the difference between those directions there. And I'm also noticing right here, because those are in a perfect line like that, that's going to be a horizontal, or not a horizontal, that's going to be a slant asymptote. So the graph is going to be, oops, just kind of coming up along the asymptote. Once it starts getting close to the asymptote, it's kind of forced. It gets sucked into the asymptote where it's just going to get closer and closer and closer to that slant asymptote there. So it is kind of difficult to sketch the solution when your tangent lines are spaced so far apart. You don't have as much information. You're not quite sure when you're supposed to turn and how much to adjust. There were, like here, it was pretty easy because the surrounding slopes all looked the same. So I knew which direction to go in. But as I got right here, those are two pretty different slopes. And so it's hard to know how to draw it. If we had slope marks that were closer together, it would be easier. So right now, we are just making a new slope mark every 1 unit in both directions here, every 1 unit. So that's pretty spaced apart. If we changed that, now you can see that it's every 0.5 units where you're getting a slope mark, and it's just a little easier to visualize what that looks like. And we could, make them even closer together. Here, we've got slope marks every 0.25 units. And here, even closer, every 0.2 units. So if we tried that again, this is the same differential equation. It's the same slope field, just with more tangent lines at more frequent intervals. And so if we go to the point negative 1, 1, I know it's a little hard to see, but here, negative 1 is here and 1 is here. So that point right there, now it's a whole lot easier to see where to draw this curve. We just go in the direction of the tangent lines and we make those adjustments as we get closer. I put a little too much of a curve at the end right there. Let's try that again. Down. Okay, so now my eye is like right here, but those are closer than they were before, so it's giving me a better idea of where to go. And then I end up like approaching that tangent, which I may be off a little bit. Where is that? It's right here. I mean, not tangent, I meant asymptote. Oops. This is that slant asymptote right there. So our graph is going to end up approaching that slant asymptote that way. Okay, for our last example here, we've got multiple parts, but the first thing we're going to do is sketch the slope field for the differential equation dy dx equals x over y. So this is not autonomous. We're going to need to consider both the x and y coordinate to produce our slope field. I do like to start by thinking about where is the slope going to equal 0. So it is a fraction, the slope or the derivative, it's a fraction, and that's going to equal 0 when the numerator is equal to 0. So wherever x is 0, we're going to have a slope of 0. So x equals 0, down this column right here. And we're going to have slope of 0 whenever x is 0, regardless of the value of y. Well, I shouldn't say regardless, actually, because if x is 0 and y is 0, we get 0 over 0, which remember is an indeterminate form. And so when you get 0 over 0, we just omit the slope mark. Okay, so I'm not even going to draw a slope mark at 0, 0, because that slope is indeterminate there. So we're just going to leave that one blank. And then when is the slope going to equal 1? Well, it's going to equal 1 whenever the x-coordinate and the y-coordinate are equal to each other, because we'll have the same number divided by itself. So when x and y are equal, except for the 0 and the 0, right? We already talked about that. So 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. And the slope would be negative 1 whenever x and y have opposite values. So like 1, negative 1, 2, negative 2, negative 1, positive 1, negative 2, positive 2. So we're getting an interesting pattern here. Kind of looks, we've got an X shape going. And for the rest of the points, we might just have to plot. So let's start in quadrant 2. I'll just start in the upper left-hand corner. Negative 2 and 3, the slope is going to be negative 2/3. So for negative 2/3, I'm visualizing, okay, from right here, negative 2/3, I'm going to go down 2 and write 3, and that's going to give me, the angle. And so I'll draw my slope mark at that angle right there. If I can picture what that was. Down 2 over 3. So it's about like that. Okay, then negative 2, 1. Negative 2, 1 is going to be slope of negative 2. So I'm just going to estimate, and I'm thinking like go down 2 over 1 and see what angle you're getting there. That's the angle to draw your slope. Negative 2, 0. Well, the y can't be 0. If y is 0, we get something that's undefined. So as long as it's not 0 over 0, we can assume that we're going to have a vertical tangent. So at negative 2, 0, we have negative 2 over 0, and that means that the slope is approaching negative infinity there. So we will draw it as a vertical tangent. If it's 0 over 0, you just omit the mark altogether. Okay, negative 2, negative 1 is going to be a slope of 2. So I'm going up 2 over 1. That's the angle that I'm picturing there. And negative 2, negative 3 will be positive 2/3. So up 2 and over 3. That's the angle that I'm picturing there. 2, 3. Oh, up 2 over 3, right? It's more like that angle. And it's okay if it's not perfect. Negative 1, 2 is negative 1/2, so down 1 over 2. Negative 1, 3, be down 1 over 3. Negative 1, 0. Well, when y is 0, we're going to get vertical marks here, except for the 0 over 0. All right, and then the rest of the points, they are going to be symmetric. So if you're, good at visualizing the symmetry, if you just kind of reflect these points, then you might be able to fill them in quickly. Otherwise, just go ahead and compute them. So 1, 2 is going to be a slope of 1/2. And then this is going to be 1/3, so it's going to be less steep, and then even less steep. At 2, 1, we have a slope of 2. So we're going to be like that. 2, negative 1, slope of negative 2. 1, negative 2 is going to be negative 1/2. And then those are kind of symmetric there. And then really not very steep at all. Okay, so about like so. And here's what that actually looks like, that slope field. So we did number 1, sketching the slope field. Sketch the solution curve through the point 0, negative 1. So here's the point 0, negative 1. And we have a horizontal tangent right there. So that's going to be a relative max, I can see. And our solution is going to look like so. Looks like we do have a slant asymptote right here, and then also right here, which leads me to believe this is probably a hyperbola, meaning we probably have another like matching piece up here. But since we only have the one initial condition, we won't make that assumption. Okay, find the particular solution to the differential equation with the initial condition f of 0 equals -1. So I'm going to come back up here and I'm going to solve this differential equation. We're going to multiply both sides by y, and we're going to multiply both sides by dx. So y dy equals x dx. Then we can integrate both sides. So get y squared over 2 equals x squared over 2 plus our constant c. Multiply both sides by 2. We get y squared equals x squared plus 2c. Now 2 times c is still a constant, so I'm going to call it c, but then I have to rename the old constant. So there's my general solution. And then if I want to isolate the y equals, now I don't know if it's plus or minus, I actually do, but I'm just saying in general, you have to consider the possibility that it's plus or minus. And look at your initial condition, right? So it could be plus there, it could be minus. But the initial condition says that f of 0, which is a y value, has to equal -1. And the only way that this y value can equal a negative number is if there's a negative in front of the square root, because the square root of something is always positive. The square root of something cannot produce a negative number. There. So there's my general solution. To get the particular solution, we are going to substitute in x equals 0 and y equals -1. So -1 equals negative square root 0 squared plus c. Square both sides, I guess, or maybe it might have been easier to even substitute in here instead. -1 equals negative root c. Oh yeah, square both sides. 1 equals c. Okay, and that means that our particular solution, so coming from the general solution, we're just going to substitute 1 in for c. Y equals negative square root x squared plus 1. So this is the particular solution, meaning if you were to graph this on your calculator, negative square root x squared plus 1, it should look exactly like the graph that we sketched here if we did a good job with our sketch. That is supposed to mimic this solution. So if you want to check that by graphing, I would suggest you change your window settings to just go from x equals -2 to x equals +2, and then y from -3 to +3, and make sure that this graph of this equation here looks like the graph that we drew for our solution in our slope field. Okay, that wraps up our lesson on slope fields. Thanks for joining. See you next time.